long time, but we should focus on the plant environment time series and the machine learning predictions. This is what I'm actually going to talk about. So, when we look at the environment, this is the greenhouse environment, this is one day, two temperatures, taken in a high resolution every few minutes, and you see a big variation between the space and the time. So if you have few plants there, each one they're going to feel a bit of a different temperature during the day. One of the organs that sense these changes the most is the stomata. And in wheat, stomata conductance is one of the best traits to yield. So as more the stomata is open, the more yield you should predict. So we wanted to monitor many lines and try to predict transpiration and stomata conductance in order to make some artificial or AI models to predict transpiration. What we did, we used the planetary system, which basically allowed us to monitor all of these traits for each line and simultaneously control the irrigation and nutrient treatment. Why is this important? Because if you take the measurement of a person, the physiological measurement, it doesn't work as much for AI because you don't have the tagging. You don't know if you were sleeping or walking or eating. But if you monitor its physiological plus you know how fast you run, then you have a tagging system. And this is exactly what the planetary system gives us. For one hand, the system controls the environmental conditions, salinity, drought, irrigation, fertigation, and so on. And from the other hand, it gives us a lot of physiological information. Regarding the experimental design, I'm not going into detail, but we use these guidelines published recently in the Journal of Experimental Botany. We use the main guidelines for the experiment. It's very important when you do drought experiment to follow these critical guidelines, otherwise you might compare different traits. And this is how the experiment looked like. So this is our digital field. We have here more than 600 plants, each one of them sitting on the plant array using the system. And each one of those been measured stomatal conductance, transpiration, biomass gain, water use efficiency, root flux, and so on. And the nice thing about it is that each of these plants is measured continuously. Every few minutes, we measure all the conditions, light, temperature, CO2, and so on. And the transpiration stomatal conductance of each plant. So we have a continuously and simultaneously comparison of all the lines. What do you do with all the data? This is a big problem. Luckily we have the AI, but when you go to the AI, you should know if you put noise or garbage, as we call it, into the data, you're going to get this garbage out. So you must filter your data, you must take care of your data. And here again, each data you measure, it doesn't matter which data you take, always count with the noise. So you must improve your signal. The signal is the blue line and the noise is the background. You must improve it. We use the Plant-Ditech filtering system, so in the end we get all of these noise out, or most of them out. And this is how the trait looks. This is the light, temperature, humidity. And here you see the plant growth, and here you see the transpiration. So you see the transpiration is much more sensitive to the environment than the plant growth, which is periodic. Altogether we collected thousands of data points for 7 years of all these plants. We run the AI models. In the end, we decided to work with the XGBoost model, and we find a very, very nice correlation. One of the most important things we found is the temperature has much more impact than the VPD. This was a big surprise because in literature you always find the VPD as number one. Skip the take-home message. I just want to thank Shani Friedman and Neil Alvarez. This is the part of the PhD, and this work was published recently. Thank you.